No questions? Oh, the review stuff? Yeah. Oh, it might have been wrong. The answers? Oh, really? Okay. I pulled that off the web. So. See if I can read. All right, number 10. I don't think I have a copy of it. Can you just tell me what it is? Yeah. Y equals 1 over. That's plus 1. Good. Minus 1. What I did was like move it up, so that's a negative 2x minus 1 to the negative 1/5. 1 to the negative 1/5. So right now you're not actually taking a derivative. Okay. You're just rewriting it using. I don't know how you guys do it. That's reasonable. Okay. Forward. And now derivative. Okay. Derivative is so power chain rule. So negative 1/5 comes out. All of this to the raised to the negative 6/5. So you're subtracting 1 from there. Good. Times 2. Yeah, that's right. Then the quote or the answers wanted to change it back down to the root. Okay, so you just left it like this. Change back to -1 to the negative 6/5. And then yeah, but then that's fine. But let's see what they have, right? Yeah. So they're just missing the 5 on the bottom. Yeah, they're over. Their answer. So this would be 5. And you have here the 5th root of 2x minus 1. You could put the 6 in here. Or you could put the whole root, the 5th root, and then the 6 on the outside. Either way. You could also take out a 2x minus 1. Get 6 factors of it. You're taking the 5th root. So you could even do something else. All right. Did they put the 5th root? They didn't take it. Okay. All right. Okay, so today we're going to finish up 3.5 inverse trig functions, and then we're going to hyperbolic functions, and that's pretty much it. In the next class, you'll have to turn in submit your online homework, right? That's going to be due Sunday midnight or something, right around midnight. The ebook, right? Everyone here should have access to the ebook. I've talked to the publisher. I know a lot of you have temporary access, right? It's a glitch. We finally figured out what it is. It has to do with the way that I'm copying my old Canvas course and bringing it over. It still thinks y'all are a different class, and they're not giving you access 2 semesters in a row. Anyway, it's a glitch. They're fixing it. They said, don't do anything on your end. Just keep going. Before the trial period ends, it'll get resolved. That's what I'm doing. All right. So, all right. So let's get down to business. I do just want to remind you that basically what we did last class was we said, okay, we've got all these inverse trig functions, right? And they should have derivatives. And so we established what those derivatives were, right? We proved a few of them. For the homework, you have to prove a few more, but there's 6 total, right? And it's just, once you have those, everything else that we learned in Cal 1 will now apply. So any sort of chain rules, product rules, quotient rules that involve those inverse trig functions, you have to, employ when you're trying to do a derivative, right? So the thing we didn't do last time, finishing off the notes, is we did not do an example of a problem where we would have implicit differentiation. So let me, what the heck, there we go. There it is. So I wanted to do a problem like this one here. We have find the equation of the tangent line. So find the equation of the tangent line to this curve, inverse sine of xy squared equals x plus y at the point 0, 0, 0. So, okay, so just to kind of give you an idea of what we're doing here, I'm going to go ahead and pass the attendance. I'll collect those syllabus confirmation things in a moment. So what we're doing here is we are taking, did I give you the wrong one? My eyes are getting bad. Okay. So what we're doing is we're looking at the graph of this curve, which I'm going to try here, arc sine of x times y squared equals x plus y. There's the graph. I know that's kind of hard to see over here on this end of the room, but this is the graph of that relationship, okay? And what we want to try and do is find the equation of the line that is tangent to this curve at the point 0, 0. So at the origin, we want to know the tangent or the equation of that line. I'm going to guess it's y equals negative x. That's what it looks like to me, right? Do y'all see that? That it looks like it's just going to be the negative x function. But let's do it. Let's actually verify it. Now, what we cannot do here is we cannot solve this equation for y, right? We can't get y isolated by itself and then do a standard derivative. We have to use implicit differentiation. So I'm going to do implicit now. Right, implicit differentiation. So I'm going to take the derivative with respect to x on both sides of the equation. d dx of arc sine of xy squared. And then whatever I do the left side, I have to do the right side. Let's do the right side first, because I think the right side's easier. What are you going to do is take the derivative of the sum of two things. Do them individually, right? Okay, so what would be the derivative of x with respect to x? 1. Okay, what would be the derivative of y with respect to x? dy dx or y prime, whichever notation you prefer. So let me just move over here. Equals the right side should just be 1 plus, what do you want? dy dx or do you want y prime? I don't care. Take a vote. dy dx? Ooh, that's a lot. Okay, I think dy dx is going to have it. A lot of my videos I use y prime when I'm doing implicit. But when you get to related rates, you want to use this notation. So, all right, so that's the right side. Now, the left side, we have an inverse sine, right, of something. So we have composition, we're going to need chain rules. So we start with the outer function, right? What's the derivative of arc sine of anything? Well, we learned that last time. What is it? Over square root of 1 minus, and then in the formula, it's x squared, right? But for us, we don't have x, we actually have that whole thing, right? So it's going to be all of that squared right here. So xy squared. Okay, that's the derivative of arc sine. Chain rule, so times, now we take the derivative of this part that's in here. So what will we have to use to take derivative of what's in there? Product, right? You'll see the product rule. So let's just kind of look at it on the side over here. If I have x times y squared and I'm taking the derivative of this using the product rule, again, everyone's got a little bit different formulas the way they learned it in Cal 1. I'm going to always do derivative of this times this plus derivative of this times this. That's the way I'm going to do it, all right? So what is the derivative of x with respect to x? 1 times y squared. So that's going to be the first thing I have here. I need it in parentheses because I'm going to have more than one term. So 1 times y squared plus, now the part that people have trouble with, what's the derivative of y squared with respect to x? 2y, right? So the 2 comes down, 2y, and then dy dx. Okay? All right, so 2y dy dx, I'm out of room. Dy dx. And I'm not done, right? Because I then need to multiply by x to finish off the product. Equals 1 plus dy. All right. There we go. That is our derivative. Well, that is the implicit differentiation. Now, we want to find the equation of the line that is tangent to this curve at this point, right? So we know that for any tangent line, we have a generic formula, right, that we always use. The formula is always going to be y minus y1 equals m times x minus x1, right? That's, in Cal 1, we use that a lot, right, to find equations of tangent lines. If we have a point, we can just plug in the point right here, which we have, right, 0, 0. All we need is the slope. But the slope is the derivative, right, at that point. So I know what this is. I know what this is. This is the only thing I don't know. So to get that, one thing you could do, you could take this equation and solve for dy dx, right? Move things around, algebra. Fine, you can do that right now. What's easier when you actually have the point is at this point to just plug in 0 for x and 0 for y. Okay, into this equation. Replace all your x's and y's with zeros. It's easier than having to do all the algebra to get dy dx by itself. So at this point, I'm going to say at the point 0, 0, right? We get this. This equation turns into, let's do it, 1 over the square root of, okay, if this is zeros in here, right, for x and y, all that's gone. All I have on the bottom is, 1 minus 0, which is going to be 1. Okay, what about all this? Times, okay, all of that. 1 times, well, that's 0, right? So that's 0. And then isn't this plus, isn't all that 0 as well? Isn't this easier than having to solve for dy dx so far? Equals, okay, this side is 1 plus dy dx. You can't do anything over here, right? There's no x's or y's to plug in. So what's the left side of the equation become? 0, okay. So 0 equals 1 plus dy dx. And we're trying to solve for dy dx. Just subtract 1 on both sides, and you have -1, right? So -1 equals dy dx. And hopefully you just, I'm kind of assuming that you realize that this is the slope of that tangent line, right? And that is the actual slope. This is m. The m we're looking for right here. So I can just plug everything in now. Y minus y1 is the point, the y coordinate of the point, 0. The slope we just found, -1. X minus the x coordinate of the point we're given, 0. If you clean all this up, you're just going to get y as -x, which is what I said it kind of looked like. To verify it, I'm just going to graph it. Y equals -x. There it is. You confirm that we have found the equation of the line that is tangent to that curve at that point. So this should all look familiar to you. Implicit differentiation, right? Finding equations of tangent lines, that should all be something you're familiar with. The only difference in this problem is that we needed to know how to take that derivative of the arc sine part. Okay? Questions? All right, the next thing we're going to do is a related rate problem. So let's see. It's over here. Let me make it a little bigger. What is that? I think it always pops up. Let's make this bigger. Okay, a rocket It's fired straight up, has a speed of 1,000 miles per hour. Okay? Right? It takes off straight up. Who's a mile away from the launch point is tracking the rocket with binoculars. Okay, watching this rocket go. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? And then I ask what that is in degrees per second. All right, a rocket, 1,000 miles per hour, an observer 1 mile away, binoculars watching it. At exactly the moment the rocket is 3 miles high, how fast is the observer's head twisting, turning to keep up with the rocket? That's the question at that exact instant. And then we'll convert that answer into degrees per second. All right, let's get this going. This is a related rate problem. Cal 1, you loved these, right? These were your favorite problems. Do this problem without anything that we learned last class. We do not need what we learned last class to solve this problem, all right? But you'll see why we're doing it. So now everyone here has learned related rates a different way, right? Everybody has a different, the way it was presented to them, right? In my Cal 1 classes, what I provide them when we're learning this is this, where is it? Where is it? I swear it was here. Okay, I'll have to see where I put that. I don't know where I put it. Well, let's do this instead. Why doesn't somebody who didn't have me for class tell me how they learned to do this? What do you start with?
Listing what you're given and what's unknown.
Okay, so you want to write down, like, what are you given in the problem? What are you trying to find, right? Good. What else? Just draw a picture, right? So we want to draw a picture. We want to kind of see what's going on, right? So let's draw a picture first, right? So you're going to draw maybe the ground, right? And then you have your observer over here. And then you've got some rocket that's been fired up. Here's your rocket. Right. Straight up. So I always tell my students in Cal 1 that you're going to draw two pictures. You're going to draw a picture of the general situation where everything is in motion. And then you're going to draw another picture, which is the snapshot picture of the moment in time we're talking about. So I'm going to call this picture here my general picture. My Cal 1 students, I have a worksheet for this, right, that I gave y'all, and I'll provide it to everyone. It's just a little template to do these problems. So here's a general picture. Here's the picture at the instant in time. So in the general picture, you have to imagine this rocket is moving, right? In motion, straight up. Now this guy's not moving, he's just standing there. And one thing I could say is from the launch point, right, directly below the rocket, I can say that this distance is 1 mile. That's not changing, right? So I can draw it in this picture. Was it? Well, go back. How far away was the observer? An observer who is a mile away from the launch point, right? The 3 miles will come into play, but not yet. Let me make this smaller so maybe we can see the whole thing. That's too small, but so really irritating. I probably disable that, can't I, somehow? All right, so here's my picture of the instant in time. The instant in time, I still have the observer here, right? The rocket was launched, but now how high is the rocket? Here's the question. We're saying at the moment that the rocket is 3 miles high, that's when I'm going to take the snapshot and try to figure out how fast the observer's head is twisting or turning, right? So I can say from here that this is 3 miles. I can also say that this is 1 mile. That has not changed, right? Now it's not growing to scale, obviously. But that's kind of at the moment in time that we're talking about, that's what's going on, right? Right. And if I draw it like that and think about the things that are in motion, the distance from here to here is actually changing, right? The rocket's going up. Over there, it's fixed at 3 because that's the moment in time. But in this picture, it's in motion. So I'm going to assign a variable to that. I'm going to assign, I don't know, I'm going to call it y because y is usually our vertical distance. You can call this anything you want, right? But in this picture, y can be a lot of things, right? When it started on the ground, or it could be 3 miles, or it could be 100 miles. Everything's in motion over there. Right? The other things we want to put down here, what are we given in the problem? What do we want? All right, so what are we given? I mean, we know 1,000 miles an hour. That is a key number in this problem. 1,000 miles an hour is a speed, right? A speed is a derivative, right? The derivative is a velocity. So this is actually the 1,000 miles per hour. It's actually the rate of change of what variable in this picture? Of y. And now, if I had not drawn a y, you wouldn't be able to talk about a variable, would you? I needed to put the y on there. That way, over here, I can say that this represents my change in y with respect to what? Time. Okay. The rate at which y changes with respect to time is 1,000 miles per hour. Change of y, why did I use y? Well, because I labeled this y. If I had labeled it h, then it would be dh dt, right? If I labeled it r for rocket, it would be dr dt. So when you're doing these problems, it's not like step 1, step 2, step 3. You're kind of just like putting it all together in the order that your brain is working through everything. Got it? Given that, what do I want? What do I want to know? Let's look at that. At the moment the rocket is 3 miles high, so at this instant right here, how fast is the observer's angle of inclination changing? So an angle of inclination is, if you look at like horizontal, the ground, angle of inclination is this. So in this picture, I want to know how fast, remember this guy's got binoculars and watching the rocket. So I want to know how fast that's opening up, right? That angle. So over here in this picture, it's changing, right? In that picture, it's not. That's a snapshot, nothing's changing. So over here, I'm gonna have to draw a line that connects from the rocket to the person. That's our angle, and I should call it what? Probably theta. We've always used like theta or beta or something like that for angles. Over here, it's theta. Over here, it actually has a value, doesn't it? I don't know exactly what it is yet, but I should be able to get it, right? Using pre-calc, because I have the opposite side and the adjacent side with right triangle. You see the right triangle, yes. So if you have opposite and adjacent, that's tangent. So you should be able to recover the angle using some tangent function or something like that. So I want to know how fast that angle is changing. So I want to know the rate at which theta changes with respect to time, right? That's what I want to know. And I want to know it at exactly the moment what? At exactly the moment the rocket's 3 miles high, right? So at exactly the moment that y is 3. Yes. Well, it's a picture, it's a snapshot that we take, right? The rocket is moving, but we're saying like at that instant, if you were to take a picture, right? If you take a picture right now and snapshot, this angle's not moving in the picture, right? Now, 1 instant later, it's changed, right? But with related rates, we're always trying to figure out how fast something is changing at an instant, at an instant time. Are we good? No questions? This is where we have to come up with the next part, which is to get an equation. We need to somehow At this point, since we know what we're given, we know what we want, and we have pretty good picture drawn, we need to figure out how we can relate the variable theta to the variable y in the problem. We need to come up with any equation you can think of, anything that you can think of that's going to connect y and theta together in this picture. You're not allowed to look at this picture anymore until after you've taken a derivative. You must look at this picture only. So if you think of any equation you can come up with that connects the theta and the y together. So tangent of theta is y over what? 1. Okay, so tangent theta is 1. Or sorry, tangent theta is y. Right? I have now created an equation that connects y and theta together just based on basic pre-cal principles here, right? Tangent is opposite over adjacent. So we've got an equation. Let me back up. I'm not trying to reteach related rates. All of you passed Cal 1, so you saw some related rates. But I do want to recap again the technique. You draw a picture of the general situation where everything's in motion. You draw a picture of the instant in time. You write down what you're given. You write down what you want. Once you do that, you look at the variables here. You come up with an equation connecting those two variables. Got it. Once we've got the equation, what's the next step? Take the derivative of this with respect to t, because everything here is with respect to t. All right, so we're now going to differentiate with respect to time on this equation. This is implicit differentiation, isn't it? This is implicit differentiation, taking the derivative on both sides with respect to t. Let's do the right side first. What is the derivative with respect to t of y? Well, it's dy dt, right? We actually don't know what that is, but it's dy dt. Now, when I see this over here, I can kind of think, I can go back and take a look over here and say, well, I'm not too unhappy to see that because I actually know what that is. That's 1,000. So I'm actually happy to see that. The other side, though, be a little different. What is the derivative with respect to t of tangent of theta? So we have to do some chain rule here, right? First, what's derivative of tangent of anything? Secant squared, right? So we have secant squared theta, right? But then times, now you have to take derivative of the theta with respect to t, which is d theta dt. Questions on that? That's your derivative. Let's take a step back, take a look at it. I'm going to kind of talk about the things that I see here. dy dt, happy to see it, right? I know it's 1,000. d theta dt. Well, that's what I'm solving for, right? So I'm happy to see that as well, right? Yeah, so I'll isolate this in a second. But now the next thing, I need to know what secant of theta is, right? I need to know what secant of theta is. And that means you can look at it two different ways. You either need to figure out what theta is, right? Figure out what theta is, and then take secant of it, or somehow you need to know what secant of theta is from your pictures here, from your drawing. So y'all see right here, I can figure out what this angle is now. I can, right? I'm going to have to use some trig. But I can figure out what this is. Theta, it's something, right? I can find it. Yeah? But it's going to require a little bit of work, right? Just a little bit of work, but I can do it. So I'm not going to, okay? This we can continue and finish. What I want you to see is this. Right? This is always tricky. I don't know how comfortable you are with this, so this is why this is tricky. The whole reason we come up with an equation that connects y and theta together, the whole reason we do it is because we know that when we take the derivative of this with respect to t, we know we're going to get a d theta dt, and we know we're going to get a dy dt. Guaranteed every time it's going to happen. because chain rule, right? It's always going to happen. So that's why we look for an equation that has theta and y, so that we can get those two things to come out. So if you can look that far ahead, you can say to yourself, wait a minute, if I take the derivative of this, I know it's secant squared theta. I know I'm going to need theta at some point, right? And I can look at my picture and say, I don't have theta, I have to work for it, right? I have to do some work for it. So in hindsight, going back to this equation, what I can do is take a different path, okay? I'm going to go to my red path instead. Instead of going here, okay, instead of doing that, I'm going to do this. I'll leave that on the board. Right here. Before I take the derivative, okay? Before I take the derivative of this, I'm going to take arctangent on both sides. Let's see why. If I take arctangent on the left, and I take arctangent on the right, right? That's what would happen. What does the left side become? Theta. And the right side becomes arctangent y. Okay, those equations are equivalent, right? To say that y is, or sorry, yeah, to say y is equal to tangent theta is equivalent to saying that theta is equal to arctangent of y. I can take the derivative of this or that. It's up to me. What is better about this? Taking the derivative. Let's see if you can see it before we do it. What's the derivative of the left side with respect to t? D theta dt. I'm happy to see that. In fact, that's what I'm trying to solve for. And it's already isolated, right? But even better, what's the derivative of this? Let's just do it. Taking derivative with respect to t. D theta dt, right? What's derivative of arctangent of something? So this is the formula I wrote on the board. Remember, I put a little box with stars on it. 1 over 1 plus whatever was here squared, right? Okay. Now chain rule times the derivative of the y, right? Which is dy dt. What is better about that than this? Compare that and that together. What's better? You know, yeah, you have nowhere in this approach, nowhere in here do you need to ever know what theta is, right? All you got to know is what y is. If you know what y is, you've got the answer. Well, guess what? I have y. See, I can't screw it up. I mean, y is given to me. Where if I go solve for theta, I might mess that up, right? There's more room for error there. So this is cleaner, better, nicer, but you have to be willing and able to do the derivative of an inverse tangent function. So the point is that you have certain related rate problems that you did in the past that might be easier to do now if you employ the inverse trig functions. Does that make sense? Okay. So let's get a final answer. I do want an answer. So this we can just continue equals, okay, 1 over 1 plus 9 times, so dy dt was 1,000. Replacing y with 3 and dy dt with 1,000. So this just comes out to be what? 100, right? 100. Now, again, some of you took Cal 1, you might notice that I've not brought my units with me the whole time. Maybe your professor said, always bring your units. I don't know, it depends on your background. But what I tell my students is that when you get to your final numerical answer, you go back to these two, you come back to this ratio, and you look at these individual, and you talk about what units those are. Theta is an angle measurement, right? And by default, it's always radians. And then time in this problem is measured in what? Hours. Everything here has been in hours. So this right here is going to be radians. I'm just going to put rad per hour. That at that instant in time when the rocket is 3 miles high, the observer is having to rotate. That angle is changing at 100 radians per hour. Last part of the question says, what is that in degrees per second? So now some dimensional analysis. How do we convert 100 radians per 1 hour into degrees per second. So we have to convert radians to degrees, and then we have to convert hours to seconds, right? So let's do the hours first. I multiply here by something that will get rid of hours. So I put an hour on top. And let's go hours to minutes first. There's 1 hour to 60 minutes, right? That will let my hours go away. And then I multiply this by, let's see, I need my minutes to go away. So minutes here and then seconds here. So 1 minute is 60 seconds. Y'all know what I'm doing here? That should get me to seconds. How do we get radians to degrees? You have to get rid of radians down here so that it'll cancel with the radians up here. And then you want degrees here. I'm just going to put DEG for degrees. So what is the conversion for radians to degrees? 180 over pi. Good. 180 degrees is equal to pi radians. Recount, right? Go on. And now we just multiply across. And I think a calculator might be in order here. So you're going to do 100 times 180, and then divide that by 60 times 60 times pi. I'm going to give a decimal approximation. I'm getting about 1.59. Anyone else get that? 1.59. I'm going to put degrees per second. That's the way I'm going to write it. See, our answer originally was in radians per hour. And I think for most students, it's hard to figure out what that really means, like radians per hour. It's like if I tell you, you know, that you run into a brick wall at 300 feet per minute. You might not be quite sure whether or not you're surviving that, right? But if I say you hit a wall at 300 miles per hour, everyone knows what 300 miles per hour is, right? So I'm just converting to degrees per second because most of us are familiar with what a degree is. And then a second, it's just easier to kind of visualize how fast that's rotating. All right, that's it. We're done. 3.5 is done. Questions? Sure. All right, the next topic, 3.6, is a whole new set of functions that normally you don't talk about in Cal 1. So I know in Cal 1, sometimes professors will talk about the inverse trig functions and their derivatives. Most of the time, we don't talk about the next group. So these are your last 6 functions. There's 6 new functions now that we need to know the derivatives of. And they're called the hyperbolic trig functions. So to get started, what I wanted to do is motivate like why these functions are important. And I want to do it with, man, that is really annoying. How do I need to kill that. All right, so let me see how this is going to work. I brought some visual aids today. All right, so what I'm going to do here is I'm going to take this wire or rope. I don't think that's going to hold. We have these magnets. I want to go strong. Find them. Yeah. All right. Anyone know what that's called? Parabola? Does it look like a parabola to you? Yeah. So the question is, if you hang a wire between two poles, let's say, the shape that it makes, is it a parabola? That's the question. It seems like it probably is. Because remember with parabolas, we can adjust them like how wide they are, if they open up or down, and we can move, up, down, left, right. So maybe there's a way that we can adjust the parabola and actually get this to work. So let's do a smaller version, or you know what? I might be able to just use. I just don't know if y'all are going to be able to see this screen. I want to do it on this over here. Is it hard to see this screen? Or is that okay? Or you can't see it, or here? How about over there? Yes. Okay. So what I'm going to do, I didn't try this before class, so I don't know how this is going to work. And try and hang it over there. I don't want to waste too much time, but what I'm going to do is I'm going to hang this on the TV, and then I'm going to mess with Desmos and see if I can't get a parabola to fit exactly over this thing. Does that make sense? I'm going to try and do it without taking some side there. So like it's this top right there. Here. How's that seem? Okay. All right. It's not perfect, but you get the idea. So can I manipulate the parabola to make it fit exactly on top of that? Is the question. So I've already put together something. And there's my parabola. And man, this is going to be hard. Let me just try and get the shape to be pretty close first. Pretty good, not bad, right? Not bad for a first try. What do I need to do? Make the number in front of the x squared part bigger, smaller, what? What's going to make that purple parabola get more narrow? Got to get it bigger. The number in front's got to be a little bit bigger. Let me see what happens here. Try that. Close it. Damn, that's pretty damn good. I'm impressed with myself here. Well, look, no matter how hard I try, I'm never going to get it to lie exactly on top of it. Never going to happen, right? It's always a little bit off. There's always going to be a little bit of difference there. Get it to like match down here, but then it's going to be off here. If I get it to match here, it's going to be off there. No matter how I manipulate the A. Remember, on a parabola can be written ax minus h squared plus k. Remember, that's the vertex form of parabola. When you adjust the h and the k, all that does is left, right, up, down. The only thing that controls the shape is the a. No matter how I do a, I'm never going to get it to land on top of that. What we need instead is a different function. And the other function is what we're about to study, is called a hyperbolic function. So let me get rid of the parabola. And I just have this terrible feeling that this is not going to work. Okay, so there is this thing called a hyperbolic cosine function. And let me see how close I am here. Okay, I need to adjust it just a little bit. Oh, I've got to go a little bigger. Okay, try that. Oh, yeah. Oh, yeah. Okay, that's pretty damn good. Let me go back to the parabola, put the parabola in here, get them out of there. Yeah, they're not on the same scale. Okay, that's all right. Do y'all feel as if that is a little better than the parabola? I mean, the parabola wasn't bad. It wasn't terrible, but that looks better, doesn't it? I'll tweak it once. So if I really spent some time, I could make it be exactly on top of that, which is what this is all about. These are called catenaries. I'll put it out here. A catenary is any wire that is freely hanging between two poles. That shape that you get, right, can only be drawn, the function that draws that shape is a hyperbolic cosine function. So what we need to do right now is establish what are the hyperbolic trig functions, like what are they, okay? And then once we know what they are, what are their derivatives, right? So what we would want to know, and this is kind of getting ahead, imagine that this is an election, you know, imagine that this is a power line, right? You go drive around, you see power lines, right, between poles. When you are connecting a power line to a pole, right? When you connect this power line to the pole, you can't just like connect it to the pole, right? Because then you have a direct ground, the electricity goes right into the ground, right? You can't have that. You have to have an insulator between the power line and the pole. So that those insulators look like, you've seen them before or no? Kind of, have y'all seen these? They're usually like gray colors, they're usually ceramic, made out of ceramic or something. And so every power line, when it comes in here, there will be a connector, okay? And then there will be a jumper that'll go to the other side and then continue the wire the other way, right? So it's always got to be off that pole. So what you would want to know as an engineer is when you hang this wire, you know how much this wire weighs, right, between these two. And you're going to have a load on that ceramic insulator, right? There's going to be a load. And so you want to know a lot of things. You want to know what that load is. You want to know what the direction is, right? Like what is the direction of that load? Is the load like more like this, or is it more like that? Like down like this or more like that? And the tighter you go, right, the less sag, the more load on that insulator. So what would be useful to us is if we actually knew this angle, right? So that angle would just be what? The slope of the tangent line to that curve there, wouldn't it? I mean, wouldn't that give you that angle? So if we could find the slope of that tangent line, we would know the angle that that insulator is going to be at, and we figure out the load. But we need to know the function to be able to find the tangent line, right? So we need to know the function for this. All right, that's the motivation. Never seen a cardinal strap used for that, huh? Well, let's do it. All right, so the beginning of 3-6 notes is where I establish what the 6 hyperbolic trig functions are. I'm going to put these on the board because even though they're in the notes, I want to be able to refer to them. So it's really weird the way we define the hyperbolic trigonometric functions. Like when you think back to pre-cal, when you're learning the trig functions, when we're trying to define like what sine is, we define it off of a right triangle. Sine is opposite over hypotenuse. And then later on, we define it for a circle as being the y-coordinate over the radius of the circle. So we have these different definitions for sine, but they're very geometric. When it comes to the hyperbolic functions, it's not as geometric. It's sort of in terms of the construction. In fact, it's a combination of exponential functions. So I'm going to write down the first one. The hyperbolic sine function, written sine with an h and an x. You can say this sine hyperbolic. You can say this hyperbolic sine. Doesn't matter where you put the hyperbolic. Before you say sine or after you say sine, it's both ways. What it is, by definition, is e to the x, okay, minus e to the negative x, and then over 2. Or if you pull that 2 out front, you write it as 1/2 e to the x minus e to the negative x. That is the definition of the hyperbolic sine function. And so most students sit there and go, what the heck? Man, this is weird, right? This is really strange. It actually turns out that it's this right here, this expression appears a lot in like differential equations. When we were studying other things, we started to see this over and over and over. It kept on showing up. And we're like, man, we're using this so much. Let's just call this something. And so we call it the sine hyperbolic. So it wasn't like this motivated that, it was that motivated this. Okay, so that is it. All right. So just to show you how this works, it's really weird. Like right now, if I ask you what's sine of 2, what are you going to do? Get your calculator out and do sine of 2, aren't you? You're going to see, you know, I'm on degree mode or radian mode. If I ask you for hyperbolic sine of 2, well, let's do this. Hyperbolic sine, yeah, let's go of 0 first. If I ask you for sine hyperbolic of 0, all you're going to do is replace the x's with zeros, right? So let's see what it is. And I'll do this one right here. So it's going to be 1/2 e to the 0 minus e to the 0, e to the negative 0, but e to the negative 0 is still e to the 0. What's e to the 0? 1, so this is half. This is 1 minus 1. 1 minus 1 is 0. So hyperbolic sine of 0 is 0. That's it. What if I wanted to know what hyperbolic sine of 2 is? Right. So you go 1/2 e squared minus e to the negative 2. And that you would need a calculator for, because no one here really can tell me accurately what e squared is. And then definitely e to the negative 2, you need a calculator for that. So I'm going to get my calculator. I'm going to do this. I'm going to get a decimal approximation. E squared. I'm going to do it all at one time here. Anybody have it yet? Yeah, that's what I got. This is approximately, whatever. This is approximately 3.63, something like that. Okay, so approximately 3.63. No questions? Look at this here. Do you see that we would ever have a domain problem? Are there any values of x you would never be able to plug into this? Like when you get to your calculator, it'd be like error. No? E, think about the e function, right? Exponential, isn't it defined everywhere? Right? So you can plug any number you want into this. Putting a negative up here, all that does is reflects the e function over the y-axis. So it's still defined everywhere. So that means that the domain of this hyperbolic function should be everything. And it also should have a graph, shouldn't it? You plug in 0, you get 0. I can graph that. You plug in 2, you get 3.63. You can graph that. Connect all the points together, you should have a picture, shouldn't you? We'll see it. We'll look at it in a minute, all right? That is the definition of hyperbolic sine. Hyperbolic cosine is almost the same thing. It is almost exactly the same thing as hyperbolic sine. There's only one difference. You all see it? Plus. That's it. That's the only difference. Hyperbolic sine has a minus. Hyperbolic cosine has a plus between them. So the way I remember it is subtraction goes with sine. That's subtract sine. And then the other one is the default other one, you know? Yeah. However your brain wants to do it, I'm just telling you that's the way I just say, okay, for the hyperbolics, sine is the subtract one. All right, so what happens here if we do cosine of 0? Cosine hyperbolic, sorry, cosine hyperbolic of 0. Look at this. We're gonna have a half, e to the 0, 1, plus e to the 0 again, 1. So now we have 1 plus 1, not 1 minus 1, right? So this is 2, but then half of 2 is 1. Any issues with domain? No, right? So we should have a picture here. Okay, back in pre-calc, what's sine of 0? 0? What's cosine of 0? 1. What's hyperbolic sine of 0? What's cosine hyperbolic of 0? No, it's coincidence. They match. Okay, good. That's less for you to have to remember, right? They coincide. All right, what is the tangent hyperbolic? So I'm going to zoom in over there so you can look at it. Tangent hyperbolic is just what you would hope it is. It's the sine hyperbolic divided by the cosine hyperbolic. All right, so let's write that down. What would that look like? If I did tangent hyperbolic x, it should be the sine hyperbolic, which is the subtract one, over the cosine hyperbolic, which would be the add one. The halves go away. And unfortunately, there's not a whole lot you can do with this. That's just what it is. Right? That's it. Don't go trying to cancel this. Don't do that now. You've come this far. Don't be doing weird algebra like that. You can't cancel these. Right? So that's it. That's what tangent hyperbolic x looks like. Are there any domain issues here? Not up there, right? No issues. Not down here, no issues. But can this ever be 0 down here? Because you might get division by 0. Can that ever be 0? No, because that by itself has to be at least a positive number. You're going to add to it another positive number. And so when you add them, there's no way that's ever 0. So this should have a domain of everything. All right, so what are the other functions? The hyperbolic, cosine, hyperbolic, secant, cotangents, and all these flipped over, right? That's all it is. All the reciprocals of all these. All right, I'm going to look at the graphs. Zoomed in too much. Oops. You were looking there. Oh, I need to get my catenary out of there. What you're looking at there is doesn't look anything like a sine function. Does that look like a sine function? No. Okay, the hyperbolic trig functions look nothing like their counterparts. All right? That's what it looks like. It's not periodic, right? There's no, not like the sine wave, not at all. Okay, that's just the way it is. I'll zoom out a little bit. There. Okay, so that's what it looks like. All right, let's look at the cosine hyperbolic compared to that one. Huh. Very different, right? Very different graph. But that's your hanging wire, okay? That's your hanging wire right there. Now, I'm not going to prove to you in this class why it's that, but you're just going to take on faith that's what it is, all right? That's something that can be done in a DiffyQ class. You could prove the catenary is the hanging wire shape. The tangent, let's look at the tangent hyperbolic. Interesting. Let me just, again, that's all three of them. Red is sine, green is cosine hyperbolic, tangent hyperbolic is the blue. Let's look at their reciprocals. Okay, I want you to think about this before I graph it. What would the reciprocal of the sine be? Cosecant hyperbolic, right? So if you take this, do 1 over this, take every value here and 1 divided by it, are we ever going to have a problem? At 0, right? At 0, that function is 0. So if you try to do 1 over 0, it's going to be undefined, which means that when I graph this cosecant hyperbolic, you should have a vertical asymptote somewhere, right? At the origin. There it is. cosecant, the hanging wire. If I do the reciprocal of that, 1 over that, is it ever going to be undefined? Is that function ever 0? No. So when I do the reciprocal, I should not have a very class node anywhere. Almost looks like a bell curve, kind of cool. And then the cosine hyperbolic, or cotangent hyperbolic up there. So the whole point of me showing you the graphs is just so you realize that all of these hyperbolic trig functions have graphs. Some of them have domain restrictions, some of them don't. But they don't look anything like the trig functions from pre-cal, all right? Now, what we're interested in this class, is not the functions. We're interested in their derivatives, right? Now we have this new category of functions. Can we do derivatives? Let's see if I can do this. Oh, I wanted to show that this. Yeah, let's do that before we do the derivatives. You probably remember in pre-cal that when we did trig functions, you had all these freaking identities, right? Remember having to prove identities in pre-cal was brutal, right? Start with the left side, make it look like the right side. It was like really, really challenging stuff. Well, with the hyperbolic trig functions, there are identities as well. And this one is a very important one. And I want us to show it, all right? So recall from pre-cal, the identity that everyone here should be comfortable with. Everyone knows this one, right? Sine squared x plus cosine squared x is 1. I mean, that's one that you have to know, right? That's with the regular old trig functions. Look at this one. Cosine hyperbolic squared x minus sine hyperbolic squared x is 1. That's not the identity. That's not what we wish it was, right? Don't we kind of wish that this would have been like plus between those two and it equals 1? That's not the case. Subtraction, and with subtraction, the order matters, right? So we want to show that that's true. Ready? I'm going to show it's true. So I'm going to just start writing the definitions of these. This means take 1/2 e to the x plus e to the negative x. Take that. Square, right? So what's in black there is cosine hyperbolic by definition. And then I'm going to subtract from that the sine hyperbolic square, which is 1/2 e to the x subtract minus e to the negative x. Okay, now I'm going to square that. I need to show that that's equal to 1. Okay, so I'm starting with the left-hand side here. Remember how you verify identities? You always start with one side and make it turn into the other side. So I'm starting here with the left-hand side, and eventually it's going to turn into the right-hand side, which it should be 1. So let's square this. If I square this, because there's multiplication, I can square the half, right? So it's 1/4. And then I have to square this, right? And I'll do that on the side over here. If I take e to the x plus e to the negative x, and I square it, that means I'm going to multiply it times itself. Right? Let's take our time through this one. What's this? What's e to the x times e to the x? E to the x squared, you could write it that way, e to the x squared. But what's another way you could write that? E to the 2x, exactly. E to the 2x. Because when you have something to a power, you can multiply these two powers together, and x times 2 is 2x. So y'all comfortable with that idea? You multiply these two together, yes. Good. I can tell on you guys something a little different. Okay. I was listening. Gotcha. Okay, so that's the first part. Okay, how about this one? This one's interesting, here to here. So that's e to the x times e to the negative x, right? That's what that is. Same base, multiplying. Exponents we add together, don't we? You add the exponents. What's x plus negative x? 0. Right? So this is e to the 0. which is 1. Right? So when I go from here to here, I get 1. Getting kind of sloppy here. Let me move this down. This, got e to the 2x plus. So I've done the first two multiplications. E to the 2x was this. Here to here gives me plus 1. How about the middle terms? These two together. Same thing. So plus 1 again. And then finally, these two together. E to the negative x times e to the negative x. You add the exponents, you get negative 2x. So plus e to the negative 2x. These two? No. All right, do y'all buy that though? Yes. Remember, all of this right here, all that was this, right? I squared the 1/2, got this, then I squared this, and that's that over there, right? So I'm about to put that here. That's going to be an e to the 2x plus 2 plus e to the negative 2x. I put the 1 plus 1 together. Is that all right, everyone? Like that? Minus, now I square the 1/2, got a 4th. And then this one is going to be very similar to what we just did, right? Very similar. But instead of having pluses here, we have minuses. So I'll do it over there. Yeah. So we're doing e to the x minus e to the negative x times itself, e to the x minus e to the negative x. Here to here, e to the 2x. Okay, here to here. Minus 1 though, right? This time it's minus 1 because you're doing a positive times a negative. So you get minus 1, right? And then when you do the middle one, minus 1 as well. And then when you do the last one, 2 negatives would be plus, and then e to the negative 2x. Are we good or not? Yes? Yes. Plus 1 and minus 1.
Yeah, the e to the negative x.
Oh, over here. Why am I getting plus 1 here and minus? Oh, because let's see, this one came from this being multiplied times this, right? This is a positive because it's like a 1 in front of that, right? And here this is a plus 1. So my answer should be plus. Oh. But here, when I multiply this, that's a plus 1 in front. But when I multiply this one, see it's negative. Oh, yeah, okay, gotcha. Those are going to become e to the 0, which will turn into a 1, but then the sign out front was determined by the numbers in front of us. Good. All right. Keep going. Thank you for asking your question. Appreciate it. E to the negative 2x. All right. What do you think? Distribute through the 1/4 on both of those? So if I distribute 1/4 through, I'll get 1/4 e to the 2x plus a 1/2, because 1/4 of 2 is a 1/2. And then plus 1/4 e to the negative 2x, right? That's just distributing 1/4 through here. Now I have to distribute a negative 1/4 through these, right? So when I distribute that negative 1/4 through, I get negative 1/4 e to the 2x. And then, here is that, negative 1/4 e to x, negative 1/4 times negative 2, plus a 1/2. And then the final term, negative 1/4 times this one. So negative 1/4 e to the negative 2x. Who sees what happens now? Everything cancels except the halves, right? Everything cancels to halves. This term and this term are exactly the same, but they have negative. One's positive, one's negative. And this one right here, 1/4 e to the negative 2x minus 1/4 e to the negative 2x cancels. You get 1/2 plus 1/2, and 1/2 plus 1/2 is 1. And that is the right-hand side. And we have verified the identity. Okay. Questions? I'm glad you're doing that, sir. I have no problem if people take pictures during class. Okay, the only thing I ask is no video. And that's only because I don't want you to be doing videos of, you know, people in the class. That's kind of creepy, right? If you do a picture, just make sure you're doing the board and not people in the class. Okay. There are a bunch of identities. There's a bunch of identities that you could prove using similar methods. All right. And in your homework, I believe there are a few that you're asked to do. All right. I do not have time to go through all of these identities. We just need to realize that they exist. Just like in Trig Cal, we have identities. We have important ones here. This is like one of the big ones. And then those are some of the other big ones. All right. Now, derivatives. What do you think? I'm just curious. What do you think? Let me write them up here. And then you can tell me what you think the derivatives are. I should probably say, what do you hope they, right? You hope they match the other ones, right? All right, so derivatives of the hyperbolics. That's one word, sorry. So what do you say we take sine hyperbolic x, right? And we say, what's its derivative, right? What's its derivative? Well, what do you hope it is? Cosine hyperbolic x, that's what you hope it is, right? Well, we can actually prove what it is, because isn't this the same as saying, what's the derivative of 1/2 e to the x minus e to the negative x? I mean, that is what sine hyperbolic is, right? And so asking what the derivative of this is just really asking what's the derivative of that. And let's do that. We can do this derivative. The 1/2 out here is a constant, right? So it can just come down. I'm taking the derivative now. Okay, let's do these term by term. What's the derivative of e to the x? Itself. Okay, great. Okay, minus comes here. Now, cover everything up. E to the negative x. What's its derivative? Itself, right? Itself times -1. Where's that -1 coming from? You have to do chain rule and take derivative of what's up here. Yeah? So the derivative of this is really negative e to the negative x. That's another way I can write that. That's what would go here, right? So we have this minus here, but then that's a negative, isn't it? So it's going to be minus e to the negative x. And now these two minuses become plus, right? So this becomes 1/2 e to the x plus e to the negative x. And what is that? That's cosine hyperbolic. So yes, indeed, the derivative of sine hyperbolic of x is cosine hyperbolic x. All right, do you understand that? All right, I'm going to give you 6 minutes. You can work together. Separate piece of paper, put your name on it. You're going to prove the same way I did this. You're going to show me what the derivative of cosine hyperbolic is. Right? I'm going to leave this on the board. Set up, write cosine hyperbolic x, write out what it is by definition, take the derivative, and then draw the conclusion. What is it? What do you hope it is? What do you hope the derivative of cosine hyperbolic x is? Negative sine hyperbolic. That's what you hope it is. Let's see if it is. Everyone understand the assignment? Say group quiz. Group task. Fun project. Yes. So what I'm asking you to do is take cosine hyperbolic x, and I want to know what the derivative is. Doing it the same way I did here. Do you all understand the question? Clarify. You can work together. Talk to your neighbors. Make a lifelong friend today. Let's see if y'all can finish that in 6 minutes. When you're done, you can come put it up here. Okay? Right here in the corner of my desk. With that little paper I gave you. Step out for a minute. We'll talk to each other. You want me to wait? Okay, yeah. Like that, no? Yeah. Oh. So you have to take 281 to get out of stomach. So you come with that. Yeah. Yeah. Right. Everybody got it or no? Yes. Everyone's turned in. So what is the derivative of cosine hyperbolic? Sine hyperbolic, right? Not negative sine hyperbolic, as we would wish, right? The derivative of sine hyperbolic x, cosine hyperbolic x, that's what we would want. The derivative of cosine hyperbolic x, sine hyperbolic x, not no negative. That's the way it is, okay? Now, how would we figure out the derivative of sin hyperbolic x? We could go back to the definition, right, with all the e's. But remember how ugly tangent hyperbolic was? Why not instead, why don't we do this way? Rewrite this as sine hyperbolic x over cosine hyperbolic x and take its derivative and do quotient rule. Right? The quotient rule. What's the derivative of the top? Cosine hyperbolic x times the bottom. Cosine hyperbolic x, right? Minus derivative of the bottom, which is sine hyperbolic x, times the top, sine hyperbolic x, all over cosine hyperbolic x squared. Right? Any questions on that? Sure, I'm just doing quotient rule there. Does anybody recognize the numerator? What is it? The identity. So what is numerator? 1. Right? Isn't this cosine squared hyperbolic minus sine squared hyperbolic? And didn't we prove that that's 1? So this is really 1 over cosine hyperbolic squared x, which is 1 over cosine is secant. So this is secant hyperbolic squared x. Hey, isn't that the derivative of tangent? In count 1, derivative of tangent theta is secant squared theta. Well, guess what? The derivative of tangent hyperbolic x is actually secant squared hyperbolic x. So that one matches up, right? And we could keep going, right? We could do the rest. But these are all on your formula sheets, okay? Here they are. Here are the derivatives. But they're on your formula sheets. Remember, on your formulas, you've got these derivatives right here now. It's formulas 25 through 30 are all of your derivatives of your hyperbolics. Okay? So you don't have to memorize these, but they're not that hard to memorize the sine and cosine hyperbolic ones. Also, on your formula sheets, right here on the page, reference page 4, there is the definition of the hyperbolics with the E in there. And it also has, I think there's a few of the identities on here. What? Maybe I'm wrong. Thought there were some identities. I guess not. Yeah, okay. Y'all doing all right? We got 15 more minutes. All right, so a quick recap. We have from pre-cal, we have 6 trig functions: sine, cosine, tangent, secant, cosecant, cotangent, right? Then we have their derivatives. From last class, we have the inverse trig functions, right? There's 6 of them: arc sine, arc tan, arc cosine. There's 6, and we have 6 derivatives as well. That's 12 derivatives now, right? We have 6 more functions, hyperbolic trigs, and their derivatives. That's 6 more, right? So now we're up at 18. Each one of these functions, each one of these hyperbolic functions, not the derivatives, each one of those 6 has an inverse as well. And each of those has a derivative. And then we're done, okay? Then there's no more, we can move on to Cal 2 stuff, okay? No, I promise, that's it. That's the end, okay? So look, every one of these hyperbolic trig functions, every one of them has an inverse. So if we take sine hyperbolic x, right? We say, why is that? It has an inverse, okay? The inverse of this function is y equals sine hyperbolic inverse of this, right? And there's a relationship with domains and all that. We're not going to get into all the nitty-gritty details. We just need to know that for each of the 6 hyperbolics, right? For all our hyperbolics, there's inverses for each one. Those have derivatives. So we need to know that they have derivatives. Yes. So how does the unit circle? There is a way to connect the hyperbolics to a circle, but it's not something easy. So there's no unit circle. Is that what you're asking? Yeah, there's no. The unit circle, all of that is reserved for the standard trigonometric functions and their inverses. Yeah, these hyperbolics involve the exponential functions, right? And so we saw their graphs, they're very weird. Right. So, let's see, my notes, I want to follow my notes because there's something I do want to do. I think I'm going to run out of time on it. Let me just show you this. On your formula sheets, just get straight to it. Here were the derivatives of the hyperbolics that we just talked about. There they are. Here are the derivatives of the inverses. Right? So that's all 18 derivatives are here. Starting here on formula 13 is a derivative of sine. Then you got the derivatives of the inverse, starts at 19. Then the hyperbolics, their derivatives, and then the inverses, their derivatives. 18 total. 18? 24, sorry, we were at 18. We needed to add another 6, 24. All right? All right, we're going to do this. We're going to look at that very first one. I want to look at what the definition of this is. All right, so everyone here, we know the definition of sine hyperbolic, right? This is 1/2 parentheses e to the x minus e to the negative x, right? That's the definition of this. What is the definition of the inverse hyperbolic sine function? That is its definition. Okay? This is the definition of this function. So if you plug x into this, it'd be the same as plugging x into this. All right? I'm going to have you take this on faith for all the others. For cosine hyperbolic and tangent hyperbolic, I'm going to let you take that on faith. I'm going to show you why this is true. All right? I'm about to show you why sine hyperbolic x is this. And when I do this, when I show this to you, I'm probably going to do something algebraically that you've never seen done, which is why I want to do it. All right? I don't know. I've got 9 minutes. Let's go for it. All right. So what I want to do right now is I want to show that this is equal to this. All right. That's what I'm about to try and show you. Okay. So let's start out with this. Let's start out with y equals sine hyperbolic inverse of x. I want to know what that is algebraically. I have no idea right now, right? So what I do know, though, is this. If I take the hyperbolic sine on both sides of the equation, right? If I take hyperbolic sine on both sides of the equation, I'll get hyperbolic sine of y, and then when I put the hyperbolic sine together with its own inverse, it will kill off everything and become the x. Do you follow that? Fair? Okay. Now, oh, you know what I should do? If maybe I should do it a slightly different way. Make this easier. Let me do this. Do you remember this from college algebra? Let's say I had a function like this. There's a function, right? And if I asked you to find its inverse, do you remember the method? You would call this y. You would switch the x and y, right? You'd make this x, make this y, and then you solve that for y. Do y'all remember that method? Okay, move the 1 over, divide both sides by 3. You solve for y, and now whatever this is, that is your inverse function. So that's how we find inverse functions in college algebra. Replace f of x with y, switch the x and y, solve for y, replace y with f inverse. These two functions, if you compose them together, they kill each other off. Do you remember that method? Okay, let's do that instead of this. So I want to start here with the original function, which is this, right? Sorry, this one. We're trying to find the inverse of this, right? Inverse of this. So let's start here with y equals. I could have gone the other way, but I think this is more. This gonna lend. I think since you know this, I think this will work out. Okay. So I want to find the inverse of that function. So what do? Switch x and y. Have y'all realized that's the line I just erased? Okay, let's get into it a different way. All right, now what do I need to do? Solve for y. How? You can't. I mean, unless you take the hyperbolic inverse on both sides, but you don't know what that is, right? That's what we're trying to solve for. So how do you solve for y? You don't have an easy way. I'm talking fast because I don't have much time. So what I'm going to do is I'm going to write the definition of what the right side is. That's the right side by definition, right? That's what hyperbolic inverse, that's what hyperbolic sine of y is. Now I'm going to go try and solve for y, all right? So the first thing I'm going to do is multiply both sides by 2. And what that does is just freeze these up. All right? This is where I normally in class, if I have enough time, I let y'all work in groups to see if anybody can figure out how to solve for y. And in my 20 years of doing this, I've only had 2 students ever figure it out. So I want to give that to you, but I think I also have time restrictions here. Maybe I'll give you a minute to look at it. How would you solve for y? Yes. Well, yeah, I kind of put it up on the board. Yeah, so natural log seems reasonable because natural logs will kill off e's, right? The question is when. Can I do a natural log right now? Let me just see what would happen. If I did natural log of 2x, so I have to do it on both sides, right? And then I do natural log of e to the y minus e to the negative y. The problem with this is that you have natural log of 2 things being subtracted. And there's no way that you can actually simplify this. If this was multiplication, then you could use properties of logs and split it into 2 logs. And then you could use the nice property that the logs would kill off the e's. But because it's subtraction, there's nowhere you can go with this. So you get stuck. But we know there's a natural log because of the answer, right? So this is kind of like, Not going to work. That would be a natural first step. Most students that get somewhere on this, that's what they want to do first. Okay. 30 more seconds. Okay, so you want to move this over. Makes it positive, right? On the other side. And then do log on both sides. Yes, that would get, okay, so let me do log on both sides right now. When I do natural log of e to the y, this indeed is going to turn into y. But the problem is you've solved for y, but it's in terms of y. See, this doesn't simplify because there's a plus. So you can't do anything over here. And so the only way to know what y is if you know what y is. And that's circular argument. You know what I mean? You haven't isolated y completely. Someone else says, no? Yeah, okay. Yeah. I mean, if we took the derivative at this point, we would get a relationship between the rate of changes of these variables, but it doesn't really get us what y is, right? So 2 minutes. Let me just do it, okay? You ready? So here's what you have to do. If you need to go, you can go. I'm going to finish this problem though. I'm going to rewrite this as e to the negative, e to the y on the bottom, 1 over e to the y. I'm going to write it like this. That's just to help you see what I'm about to do. I'm going to multiply everything, both sides of the equation, by e to the y. Okay? That's what this is, right? Okay. Multiply both sides by e to the y. So if I multiply this by e to the y, I get 2x e to the y equals, okay, now I have to multiply this side by e to the y. So distribute through, what's that? The 2y. And then what's this? Minus 1. Okay. Doesn't look like we've gotten anywhere. And this is not crazy algebra, okay? This is not something you probably have never seen. I'm just multiplying both sides by something weird, but it's still just algebra. This is the part. I'm going to move everything to one side. Okay, so I brought this term over and I stuck it in between these two, all right? Here's the algebra that most of you have never seen before. You've seen it, just not like this. I'll do one more line before I do it. Is that not the same? If you squint your eyes just to know, does this kind of look quadratic? Right now, our standard quadratic is that if we have ax squared plus bx plus c equals 0, we have the quadratic formula, right? And so we have something squared, something, right? The variable here is x squared, the variable here x to the first power. And then the a, b, and c have always just been numbers, haven't they? Not this time. This is like our x squared, right? Minus something in front of x minus number. So this is the quadratic equation. But our a, b, and c are actually what? Like, what's a for us? 1. What's b? Negative 2x. What's c? Negative 1. Okay. It's weird, yes? Weird. So now I'm going to use this quadratic formula. Remember the quadratic formula is that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, right? That's your quadratic. So I'm going to use that formula, but I'm not solving for x here. What am I solving for? E to the y, right? The thing that's being squared is e to the y. You're not going to hurt my feelings if you have to go, right? Because I realize I have to go too. I have a class, and I'm going to be late to it. So now here's what I got. E to the y equals negative b. What's negative b for us? 2x plus or minus the square root of, what's b squared? Negative 2x squared, which is 4x squared, minus 4 times A times C. So negative negative. So isn't that going to be plus 4 in here? And that's all over 2. Okay, what do these both have in common? A 4. So I can pull a 4 out as a 2. Once a 2 comes out of this, I have a 2 in all the terms. So it reduces to this. The 2 on the bottom cancels, doesn't it? Yeah. Now the natural log on both sides. Now the natural log. So if you take the natural log on the left side, what do you get? 1. Take the natural log of this and you get that, don't you? Right? But not the minus. Why is there not a minus in there? Imagine I get the natural log here, natural log here. Why am I ignoring the minus? Can't have the natural of a negative. And if you look at this, this is x, right? Imagine that 1 wasn't there. What's the square root of x squared? X, okay? So I'm doing like x minus x. But if I do plus 1, this is bigger than x. And so x minus that would be a negative number, and you can't have a log of negative. So we can't have the negative. There you go. That's some weird shit right here, isn't it? Okay, y'all have a good one. Try to do as much of your homework as you can for 3.5 and 3.6. Okay, we've covered everything. All right, I didn't do some things, but just see how it goes. All right, have a good weekend. I gotta get to class.